Hello, everyone. Thank you for joining us for our November webinar focused on green solvent solutions for flash chromatography. Today's webinar is being led by Josh Lovell, Teledyne ISCO's application specialist. If you have any questions or comments during the webinar, please utilize the chat function within the Zoom platform. And at this time, I will turn it over to Josh.
Okay, thanks, Tori. So today, like Tori said, we're going to be talking about green solvent solutions for flash chromatography. So today, we're going to be discussing considerations of green chemistry that apply to flash chromatography. What impact can greener chromatography make? How automated flash chromatography has features that allow for greener chromatography. And then finally, we'll discuss some more specific method development ideas about being greener and how you guys can help. Within those topics, we'll be discussing choosing your column and how quality, capacity, and resolution all play a role in the greenness of your method. We'll talk about one of the most important things is proper scaling of sample loading and column size in relation to greening our chemistry. And then finally, with the stationary phases, we'll discuss how functionalization of your columns can lead to greener opportunities. The next segment, we'll discuss solvent system choices and alternatives. We're going to really focus on eliminating dichloromethane as a mobile phase solvent and discuss some alternatives for dichloromethane. We're also going to discuss some reverse phase alternatives that might be useful for you. And then finally, we'll talk about some tips that can save a little bit of solvent from your runs, and every little bit adds up. So we'll discuss those. So we're going to start with the 12 design principles of green chemistry. The first one is prevention. The next one is atom economy. Third one is less hazardous chemical synthesis. Next is designing safer chemicals, safer solvents and auxiliaries. Designing for energy efficiency, the use of renewable feedstocks, reducing derivatives, catalysis, design for degradation, real-time analysis for pollution prevention, and then inherently safer chemistry for accident prevention. So these are the 12 key principles of green chemistry. So next we want to talk about which of these principles we can apply to flash chromatography. There's a few principles on there that don't really pertain to purifications and chromatography, but there are several that chromatography can have a big impact in reducing the environmental footprint. So we'll discuss those. The first one I think is obvious. It's minimizing waste through the prevention design principle. So this is reducing the amount of solvents that we use, reducing the single-use columns that we use, things like that. Next is less hazardous chemical synthesis. And so purification plays its role in synthesis. And so if we can minimize the use and amount of toxic substances, so we want to try to avoid toxic solvents, additives, things like that. Reducing and eliminating those are going to be things that can contribute to less hazardous chemical synthesis. Designing safer chemicals, and with that, designing safer processes. So purification process, are there ways that we can make it less hazardous? Decreasing exposure for chemists to solvents and things like that. So how can we make the process safer? Safer solvents and auxiliaries. So solvent choice plays a huge role. So if we can develop alternative solvents that are more benign and still useful to us, and we can substitute those in. So we'll discuss that. Another principle, designing for energy efficiency, and this actually also corresponds with a green engineering principle that I think applies to chromatography in a big way, and I think it's a good idea to remember, and it's maximizing efficiency. So meet your need and minimize your excess. And so really efficient purifications, they do this. So, if you make efficient purifications, we're going to minimize excess and waste, and we're going to meet the needs of the purification by getting our compound pure. The next thing would be use of renewable feedstocks. So as new solvent options are developed, how we implement them into the chromatography world. can be useful, or how quickly we can implement those and not drag our feet to change. Next would be inherently safer chemistry for accident prevention. So we can apply this to almost any area of chemistry. And so safety, what kind of safety features can we put into our systems to minimize exposure and risk to the chemist? So the next question is, what kind of impact can going green in Flash have on the overall E factor, or environmental footprint of the industry? So we got a nice figure here. This shows the amount of chemical waste produced in relation to product produced. And you'll notice that you compare the pharmaceutical industry to other industry sectors of chemistry, fine chemicals, bulk chemistry, and oil refining. The actual amount of waste is the least in regards to those other areas, but the actual E factor, where the amount of waste per kilogram of product, is actually the highest. So the pharmaceutical industry is actually the least efficient in regards to the E factor. And so the amount of chromatography waste generated per researcher is small compared to manufacturing or large-scale processes, but cumulatively, each chromatography purification can have if we make changes throughout and do it on each run, we can have a substantial impact on the environmental footprint. Small changes for users towards greener methods can help to substantially reduce the footprint. And currently, some estimates have solvent for purification constituting 56% of the total material to manage active pharmaceuticals. So we can see solvent for purification. This is from other modes of purification also, but chromatography is included in that 56% of the total material. So if we can make reductions in solvent, we can have a great impact in that. So next, we're going to be discussing features of automated flash chromatography that help us with green chemistry, meeting some of the green chemistry principles. So one of the things, our new Combiflash NextGen line of flash purification systems. So we've recently went back and we've looked at all our default methods, and we've reduced the solvent amount of those methods. We've made them more efficient. Also, you have the programmable gradient control so that you can modify methods on the fly, so you can optimize while the run's going. So we'll discuss that in more depth a little bit later here. Additional feature that's new to our systems is baseline correction. So this opens up additional solvent opportunities that maybe we weren't able to do chromatography with before. So it gives us more choices. Another nice feature to help with the management of reusable column types is that we have our column recognition RFID feature. And so one of the nice things about that is you can monitor the number of uses of the column, and also look at the last used conditions that were used on that column. So that's good for helping to manage those columns when you're using them. Additionally, just inherently with a lot of the flash systems, you have directed fraction collection, so you're minimizing the amount of solvent that needs evaporation, minimizing the amount of glassware that needs to be cleaned. So those all do contribute to minimizing our footprint. And then finally, our solvent management system is unique on our systems. We have active solvent level monitoring and waste level monitoring. So this helps avoid wasted runs. If your column ran dry, if you misentered data, if it wasn't monitoring the level appropriately. It also is a safety feature that allows mitigation of spill risk. So that's something that's good for safer processes. One of the things I want to go into in detail, a little bit more detail, was our solvent savings. So this is a table comparing the older generation Combiflash to our NextGen Combiflash here. And so we've made significant solvent savings in the default methods across all column sizes, some up to 50%. And so you can see 100 milliliters is saved on a 4-gram run. 1.3 liters is saved on a 330-gram run. So there's a significant amount of solvent that's saved, especially when you look at multiple runs. The solvent savings for default methods are very significant. So a new feature on the NextGen systems is the baseline correction feature. So this is on the NextGen 300, 300 plus. And basically what it does is it enables a short pre-run gradient to measure baseline absorbance. And this allows the system to go ahead and subtract the baseline from the run. And essentially what this does is it expands the detection ability across all the wavelengths of the detector, and you're not limited by solvent UV cutoff now. And we'll show some examples of that. And what this ultimately does for us is it opens up other solvent alternatives that traditionally are not used in chromatography. So maybe we're allowed greener solvent alternatives, so maybe using acetone instead of acetonitrile, or other solvents. Or maybe it allows us to do a more efficient purification. So maybe we're using a toluene because it allows us a different selectivity for our column in our system. And it actually gives us a more efficient separation. So maybe it decreases the amount of solvent that we're using to purify our compound. So you can be green in kind of some different ways there, not necessarily substitution, but reducing the amount of total solvent you're using. So how to use the baseline correction feature. So if you guys go to your method editor and you guys click the details button next to the wavelength input on the method editor, there's an option there that says baseline correction. You can go ahead and enable that. When it's enabled across all wavelengths and both set wavelengths. So if it's on for all of them. So keep that in mind. Now some examples of how this has been used. So in the lab, we went ahead and what we were interested in, we wanted to monitor the 215 nanometer wavelength, which actually overlaps with ethyl acetate. And you can see that without baseline correction, you can see the first peak, but the second peak is almost indiscernible at 215 nanometers because of the ethyl acetate competing for the absorbance there. With baseline correction on and using ethyl acetate as a solvent at 215, we're able to get very clean discernment of the peaks there at 215. So you can see there in that example, it's very nice peak shape, and the baseline is not interfering with the detection. So that's just using an existing solvent, but monitoring it at maybe a wavelength that's more important to your compounds. Another example, we've actually replaced our solvent with acetone. So this is a hexane acetone separation. And you can see on the bottom there, we have without baseline correction on, you can see that the acetone basically is absorbing at all wavelengths. The acetone is absorbing at all wavelengths, and you see the trailing baseline increasing there. With baseline correction on, obviously not a problem there in the top example, and we get good peak shape with that. So just an additional feature that expands, gives you some more choices to make your chemistry more efficient. Just wanted to show you guys quickly where the column RFID recognition in history is. So if you guys have placed a column onto the system and it's identified it, if you go to the method editor and then click on the column data button up top there on the upper right, it'll bring up a column data chart. It'll tell you what the column is. It'll tell you the rated pressure. It'll tell you the rated flow rate you should be running it at, and also tell you how many uses it's had. And then also it'll tell you when it was last used, when it was first used, and what was the fluid that was last used on it. So that way, if you're changing solvents, you can go ahead and do that without wasting solvents if you don't need to. So, additionally, just to highlight some of the safer chemistry that's allowed from by the NextGen, some of the safety features to make for safer processes, so that contributes to green chemistry. So we have our active solvent waste level sensing. One of the neat maybe things that might be useful for you is it tells you how much solvent you expect to use before a run. So this can be a way to compare maybe different methods and maybe scaling down a column for loadings and things like that, because you have an idea of how much solvent you're going to be using. It also monitors the solvent level, so it's not going to waste a run by running a column dry. Also, the safer practice with waste level sensing, stopping the run from overflowing, basically. If the container is going to overflow, it'll stop the system automatically there. Additionally, we do offer an optional vapor enclosure for use outside the hood. This is obviously going to minimize exposure to solvent vapor and decrease pollution in the lab air. We do offer a vapor sensing option. This stops the run if vapor is detected due to a leak. And then we do have light and sound alerts that let you know if the system needs attention. Okay, so we're going to get into some more of the chromatography ideas here. Discussing Let's Be Greener. It starts with a stationary phase. Then we'll discuss mobile phase decisions and other green method tips. So just kind of want to envision how we can be greener in the lab just as a overall process, thinking about, what does green chemistry look like when we apply it to chromatography? So one of the main things I think is reducing solvent usage. So we do that through more efficient methods, proper scaling, making sure that we're using appropriate column for the scale of the amount of compound that we need to purify. Make sure we're maximizing the loading per run and not wasting added resolution for no reason. If you have unnecessary resolution, you can turn that into solvent or time savings, or even going in solvent savings and by going down to a smaller column. We'll discuss that in a little more detail. Substitution with greener solvent choices. So this would be another way that we could see chromatography being greener. Decreasing column waste by reusing columns or using reusable columns. Increasing the loading capacity on the column. So choosing a high quality stationary phase is going to increase the loading. We'll go into detail with that. And then more concentrated fraction collection. So reducing the amount of solvent that we need to evaporate at the end is something that would contribute to greener chemistry, is the energy used to evaporate that has an environmental impact too. So where can I make green choices in my Flash workflow? So another way to kind of think about these things is where in the Flash workflow are my green choices? And it really starts off with choosing a column. And there's kind of two different perspectives that we kind of need to think about when we're choosing a column. One is the stationary phase type. And so this is going to kind of dictate your mobile phase system. Am I choosing a silica and am I going to be stuck with normal phase? Or am I choosing a reusable column that allows me to do either reverse or normal phase? Or am I choosing C18 that allows me to use reverse phase only? Also in this choice is the quality of the stationary phase. That's going to dictate the sample loading amount. And the next question, which is also important in choosing a column, is how big of a column do I need? And so the questions in regards to proper scaling and maximizing the loading per run is how much compound am I purifying? If I'm doing a large multi-gram purification, maybe it's wise to go ahead and do a small milligram purification on a 4-gram run, a 4-gram column, and take the 10 minutes to do a scouting run and make sure my chromatography is optimized. Maybe I can load more onto that 4-gram column and then scale that up to the larger column. So that's something that can be really useful. How difficult is the separation? How much resolution is there going to be between my compound and my impurities? That's going to dictate how much, what kind of ratio I can load my sample on. And then can I load more sample or can I run it on a smaller column? That's the kind of the ultimate question. The next thing after we've chosen a stationary phase and size for the column is choosing a mobile phase. So which solvent is going to give me the most efficient separation? And then the second question with that is there a greener solvent alternative available for that solvent system I've chosen? And we'll discuss some of those. And then third and finally, you're kind of optimizing your method. Am I interested in only one or multiple compounds? If I'm only interested in one compound, then I'm not worried about resolution elsewhere in the gradient. So maybe I can focus the gradient on the compound I'm interested in. The next question is there unnecessary resolution? So do we have added resolution that allows me to shorten my method? That's something that can shorten the run and save you solvent that way. And then finally, do I care about anything after my target compound elutes? So can I just stop the run after I've collected my compound? That's something that can save some solvent rather than going through the default gradient unnecessarily. And then finally, if you're using a reusable column, making sure that you're doing proper washing and conditioning of the column for storage so that you can reuse it instead of getting rid of it or destroying it. Okay, so going into detail here for selecting a stationary phase for flash or HPLC here. So the green impact of column efficiency. So I think this is really important, and I'm going to go ahead and kind of showcase some examples of how we can take advantage of this to contribute to greener chromatography here. And so column efficiency is really how well is the column packed, and it's a product of your particle size and how well the particles pack together. Are they spherical particles? Or are they irregular particles that don't pack together as nicely? We have two materials. We have our traditional ReadySep, and then we have our ReadySep Gold material. And our ReadySep Gold material is a smaller particle. It's spherical. It's something that has been around for a while, that we've offered for a while, that offers superior chromatography. It offers twice the resolution power and allows for twice the loading capacity and higher optimal flow rates than our traditional irregular ReadySep, which is a larger particle and not quite as nice, but it does make for an economical choice for crude purification. So, how does this translate to greener chromatography? The column stationary phase costs a little bit more for that higher material. But ultimately, by choosing the higher quality material, it allows you to use a smaller column for the same loading amount. And on the next slide, we'll show that. But ultimately, it's going to lead to solvent savings and column and cost savings. So you're buying a smaller column as opposed to a larger column with the higher quality material. So you're saving a little bit of money that way. And you're definitely going to be saving money in terms of solvent cost and time. So here's the default loading guide that we offer for our columns. So on the left there, we have our column size. And next to that column there, if we have a gold column, we have easy separation. We can load up to 20% on a gold column if the separation is easy. That same easy separation on a regular ReadySep column, we don't recommend going more than 10% loading on that. So you can double the loading on the ReadySep gold column. Also, if you have a difficult separation, 1% the loading is going to give you the maximum resolution. In that case, if we need maximum resolution, we're sacrificing loading capacity and a little bit of the greenness of and able to get the job done. So sometimes we can't make that choice because we have to maximize resolution to get our compounds pure, because that's the ultimate goal. So how can we be green with proper scaling? Principle from green engineering is maximize efficiency, meet your need, and minimize excess. And I think that defines purification efficiency very well. We want to choose the smallest column that will provide our adequate separation. So higher quality silica provides superior separation and increased loading capacity. And this leads to reduction in the solvent used, time of separation, and overall it's going to lead to cost savings. Doing a scouting run on a smaller column, like a 4 or 12 gram column, if you're doing a large amount, it's really nice because it helps you establish the loading amount, and it allows you to verify and optimize the method, make it fit your needs, achieves the goal of purification, but also then minimize the waste of the run. You can apply this to all methods, and being green can save you time and money too. So to illustrate the solvent savings by going green with the gold columns, we're going to look at this example here. So we can look at the solvent use on the right for the different column sizes. And so we're doing the same method for default ReadySep, same default method for the ReadySep and the ReadySep Gold. They're doing the same method, same flow rates, same gradient profile. So the solvent use is going to be the same for all the column sizes. But if you're able to load 2.4 grams on a ReadySep column on the right, and that's going to put you in a 24 gram column, we can actually load that onto a 12 gram ReadySep Gold column. So that's going to yield you almost 200 milliliters of savings just by going to the smaller column size. Same thing here for the going from a 40 gram to a 24 gram column. That's going to give you about 270 milliliters savings. So you can see how the savings are adding up as we go to larger columns and move down a column size here. So the loading capacity for an 80 gram ReadySep column and a 40-gram ready set gold column is the same. And so you're saving almost 650 milliliters by making that change. And so I'm going to go ahead and jump to our 220-gram column because it's a more direct comparison. But you could load 22 grams onto a 220-gram column. On our 120-gram column on a ready set gold, you could load that same amount, and you would be saving 1.7 liters of solvent in one run. So you can see how using the smaller column is going to give you less solvent used, increased concentration of your fractions, and it's going to be a cheaper column size comparably. So next I want to discuss different stationary phases for flash. And kind of the impact and some choices that you can make that might help reduce your green impact. So we have our normal phase and reverse phase stationary phases. Some of these phases actually can be used in either reverse or normal phase, like the cyano columns and the amine columns, and some of your own stationary phases that you can pack on your own and use on our systems. But normal phase is traditionally your silica, alumina, diol, cyanoamino, or amine, sorry. And then the reverse phase, you have your C18, C18AQ, cyano, and amine. So I'd like to show an example here of a stationary phase choice impacting our solvent selection. So this is a case where separation of some amines, and traditionally amines don't really travel well on silica. Particularly heterocycles without some type of additive base or using like a dichloromethane solvent. And so if you look on the left there, we have our TLC on the left with no modifier that's using hexane ethyl acetate. And it's not, it's just streaking down the column. We're not getting separation between the two compounds. They're streaking together. We use the 2% methanol with ammonium hydroxide and dichloromethane. We can actually separate the columns or the compounds out on TLC, so we get resolution that way. But it does, have some streaking still. If we use triethylamine with the hexane ethyl acetate, we're able to get a little bit of separation also, but it's not great on silica. You can see we tried to do the run on the normal phase column, silica column, using hexane ethyl acetate on the Combiflash system, and we don't get any resolution between the peaks. The peaks come out together about between 11 and 14 minutes there with no separation. Now, if we do that same solvent system but use an amine-functionalized column, we're able to get separation pretty early between A and B, and the run's done in about 9 minutes. And it comes off, right around before 50% ethyl acetate hexane. So we've really changed the selectivity of the column, and it allowed us to avoid using dichloromethane and allowed us to use a reusable column. So now we can go ahead and condition that column, wash it, condition it, and then reuse it. And we've reduced the amount of solvent that we needed to use. The runtime could have been cut in half, stopped at about 9 minutes. So you probably half the solvent, and you're also not using dichloromethane. So we've made two positive changes that we would have not been able to do if we had to use the dichloromethane method and didn't have the amine column. So this same example would apply to any other column that gave you different selectivity where you're able to get separation and avoid using dichloromethane. Another way we can go green is with reverse phases. So normal phase to reverse phase is going to give you a significant reduction in organic solvent use. So essentially you've replaced one organic solvent with water. So you've cut down the amount of organic solvent by half already by replacing it with water, or nearly half, I should say. It's also now it's a reusable column. You need to follow the care instructions for reuse though, so keep that in mind. And the other thing to keep in mind is that the loading capacity is less compared to bare silica. So the capacity is about 10% of what bare silica is due to functionalization. So if you go to those loading guides, you need to divide by 10 to get the amount that you could load on reverse phase. So the next segment I'd like to discuss is the mobile phase selection. And we can make some this is going to kind of discuss choices that'll allow us to make some substitutions. For the solid stationary phase, I think we were making mostly changes that would reduce solvent use. So that would be positive and have a big impact, but we could also substitute some solvents. So I want to go to our solvent selection chart, and we look at these different groups of selectivity for these solvents. And usually these solvents are pretty interchangeable within a group. So, you know, maybe I'm using a compound like acetonitrile. I can stay in that group and maybe use acetone instead, and stay in group 6 there. Or I can, you know, use a different alcohol in group 2 if I need to, or change from THF to 2-methyl THF in a group 3. Another one is the ethers, using a methyl tert-butyl ether instead, staying within the group. So those kind of changes make sense, staying within the same group. They're going to have similar, the solvents are going to have similar properties, and those are usually pretty safe changes. And you'll see minor changes in the selectivity, but you know, those are some reasonable choices to make. You'll see group 5 there is kind of methylene chloride by itself. So that making a change from dichloromethane isn't as obvious. But we'll discuss some research that's been done to help reduce the use of dichloromethane and alternatives for it. So some kind of solvents we're going to be discussing about how to reduce or replace dichloromethane. And so dichloromethane is great. It's a nonpolar solvent with high dissolution power. That's why we like to use it. It dissolves things really well, so we can use that as a base solvent, and it's nonpolar. The problem with it is it has high toxicity to it has toxicity to humans and also to the environment, and it's very difficult and costly to dispose of due to its low flammability and the environmental impact of it. So some other solvents we'd like to see be reduced in the lab would be acetonitrile and THF. And these are some traditional reverse phase solvents, and they have some toxicity issues that we'd like to avoid with maybe some substitution of different solvents for their use. And then another one that gets used a lot is hexane, and a lot of people have started transitioning to using heptane instead. And the reason is the toxicity and the low vapor pressure of it. So being in that environment is not as good for the chemist as using heptane, because it has a higher, because the vapor, it's not as, has a higher boiling point. So the fumes aren't as much of an issue. So now specifically, we're going to show some work that's been done to implement substitution of dichloromethane in the lab towards chromatography purifications. And so there's been some really nice work done by several different groups here. We're going to highlight one of the guides here, finding alternatives for dichloromethane methanol. And so the way that they've done this is on the lower right here, they've showed basically a relative elution strength on the bottom of dichloromethane and methanol. And these are for neutral compounds on the left here that they did some examples of. And basically they established the relative polarity of these different solvent options for you and what they relate to as far as solvent strength on the DCM methanol scale. So you could, if you had a compound that was eluting at 5% methanol in DCM, go to the 5% there on the bottom and then look up, and then you would see the corresponding solvent that would allow that similar strength of elution. And so using heptane as a base solvent and 3-to-1 ethyl acetate ethanol, it gives a pretty similar range from 0 to 15% methanol DCM. And so using that range, or using IPA or ethyl acetate instead, or some other substitutions, you can see how you can match the polarity of the solvent strength of the DCM methanol and apply that using heptane as a base solvent. Alternatively, they kind of expanded the elution strength range by using methyl tert-butyl ether. So they were using a stronger base phase, the ether versus heptane, which is going to be a stronger solvent, and then combining that with either 3-to-1 ethyl acetate ethanol or methanol to go ahead and give you a more polar base and extend the range of the relative solvent strength. One thing to keep in mind here is that there seems to be a common misconception that silica begins to dissolve in methanol above 20%. Under neutral conditions, that's not true. You can go up to 100% methanol using neutral or acidic conditions. The problem is with basic conditions, which we'll discuss in a sec. So just to be aware of. And so they also apply this for basic compounds. And what they did is they added basically 2% ammonium hydroxide to the 3-to-1 ethyl acetate ethanol mixture. And so that also gives you a pretty wide elution range. It's not quite as strong as 10-to-1 methanol ammonium hydroxide and DCM, but it's pretty similar. It gets you up to that 12% range. If you need the added solvent strength, then you can go ahead and use the 10-to-1 methanol ammonium hydroxide, but use ethyl acetate as a base solvent instead of DCM. So that seems to get you up to where that 15% basic methanol mixture would get you as far as solvent strength. You could also use the methyl tert-butyl ether again as a base solvent too, and that's going to be pretty similar. So, like I said, you need to be aware of using basic methanol above 10 to 20%. It can begin to dissolve the silica and cause some problems that way. So. Finally, the acidic compounds on the left there. So they used heptanes and 3-to-1 ethyl acetate ethanol again with 2% acetic acid added to it. And so this offered a wide range of elution strength again. It got you up to about 15% of the acetic acid, 10-to-1 acetic acid methanol DCM mixture there. And alternatively, again, you could use the ethyl acetate or the MTBE again. Not quite as wide of a range, but you could increase the polarity of the methanol there since you're under acidic conditions to kind of push it. So, so basically, the guide gives you some alternatives. It gives you a starting point. If you know what your DCM conditions are, it gives you a starting point for some consideration of different solvent conditions using the non-DCM mixture. Another study done here is using alternative green solvents instead of dichloromethane. And so this study looked at using CPME or cyclopentyl methyl ether and 2-methyl THF, tert-butyl methyl ether, dimethyl carbonate, and isopropanol ethyl acetate mixtures. And they looked at the RF ranges of these compounds and compared it to the DCM methanol. And so they looked at a broad library of compounds on the right there. I just wanted to show the kind of vast, I know that's difficult to see, but to see the vast library they looked at to establish these conditions. And say the cool thing about the cyclopentyl methyl ether and the 2-methyl THF is that they're both from renewable feedstocks. So we're going green by not also replacing DCM with some safer solvents, but we're also going green by using something that comes from a renewable feedstock. So that's something that's very positive in the green chemistry direction. And what they found was basically that cyclopentyl methyl ether is almost a direct replacement for DCM. It offers actually an extended range compared to the DCM methanol, and had similar results for similar compounds. So you'd see the same trend. The selectivities were very similar. Additionally, in another paper, which I didn't highlight here, but the reference there is on the bottom, we're actually seeing the use of cyclopentyl methyl ether and 2-methyl THF predominantly in some purification of lipids. So you're starting to see that used in some alternative specialized chemistries, but you could start to apply that to more general areas too, especially once the cost of those solvents starts to drive down. So one of the groups, some of the companies that have instituted these changes, they've been monitoring the use of dichloromethane with in concurrence with the changes, when the changes were made, and what kind of impact they had. And so one of the things that they looked at was stocking these ready-made solvents. So the 3-to-1 ethyl acetate ethanol mix, stocking that as a ready-to-go solvent, which you can actually purchase from Sigma. And then also posting the TLC guide so that they could easily go, okay, I know I have a compound that moves in 5% methanol DCM. If you have the guide there to tell you, okay, I have 3 different alternatives I could use, it's easy to kind of test that change without having to really guess around. It gives you a good starting point. And they found that these changes helped reduce DCM usage by 50% at these sites. So it's a pretty significant impact in the amount of dichloromethane that they're using, and it continues to trend down as chemists become more familiar and comfortable with these alternatives. So some other examples of choosing some different solvents instead of others in substitution. There's been several examples of using ethanol and acetone in place of acetonitrile and THF. Like I said, acetone and acetonitrile are kind of in the same solvent selectivity group, so that's a kind of a intuitive swap. Acetone is actually a stronger eluting solvent than acetonitrile, so you actually need less of that %B to move the compounds. That is a decrease in the amount of organic solvent they're using. So it's a small change, but it's a decrease still nonetheless. If you're replacing acetone with acetonitrile, or replacing acetonitrile with acetone, sorry. Additionally, I do want to point out, this is on a prep system here. This is just showing the back pressure on prep HPLC using acetone, acetonitrile, and methanol. Methanol kind of has the highest back pressure because of its viscosity. And this is a gradient with water, by the way, so it changes as the gradient changes. Acetone falls between acetonitrile and methanol. Acetonitrile is great with the back pressure and viscosity, that's why it's so popular with HPLC. But as we get more systems with higher pressure limits, especially flash systems where you're generating lower back pressures anyways because of the particle size, you could make the change from acetonitrile to acetone with no issues. The systems have increased back pressures up to 300 now for our NextGen system, and it shouldn't be a problem for those reverse phase columns using acetone. So those are some changes that you can make that would be useful. Especially on the flash side, using acetone with baseline correction, it opens up the detection options for compounds, so you're not limited by the UV cutoff of acetone as we were before. And so this is using the baseline correction on the NextGen using a water acetone gradient. And you can see we don't have the baseline drift problem we saw before in the example without baseline correction. So that's something that the baseline correction helps to solve and allow us to do. So the last section I want to kind of discuss is some other small changes you can make that can save some solvent use in your methods. So how can you make your methods greener? So in past seminars, we've discussed the importance of resolution and purification of our target compounds. And kind of the resolution is what gives us the choice of how we want to use the excess resolution. We can load more compound. We can take advantage of it to go greener by maybe making a shorter method with a focus gradient. We can shorten the gradient length to save solvent and time then. And to kind of illustrate the focusing of the gradient to help give you more resolution, we have our compound on the left, or column on the left using regular ReadySep using a default method. And then the upper right, you can see the added resolution by going to gold there. So we actually get baseline resolution between these compounds. We went ahead and did the next step there and focused the gradient on the region that elutes these compounds, and you get even better baseline resolution between them. So the question at this point is, how can I make this method greener? One, I could shorten that gradient portion up to where I start to, I keep the loading the same and I start bringing the peaks together a little bit by shortening the method, shortening the gradient portion of the method, sorry. And so I could go greener that way, or I could load more compound, or I could go to a smaller column too. So this is kind of what that information kind of can give you, what kind of choices you can make from it. So other ways you can be greener, if you're not using a reusable column, if your compound's eluting early in the method, then you can just go to end your run there after your compound's been collected. You can take advantage, ultimately the rest of the gradient is not necessary for the separation or purification, so why waste the materials? Just be sure that you let your run finish fraction collection of the peak because of the delay from the detector to the fraction collector. And you can take advantage of the end of run hold feature so the column doesn't air purge until you tell it to. So you can go ahead and maybe stop your run, check, make sure you got all your compound, and then go ahead, okay, I'm good. And then go ahead and just in the run, then go ahead and air purge and valve wash and everything. So if your compound's not done coming off yet, or you didn't get the right compound, you can just go ahead and resume your chromatography and continue the run. So in summary, what we've discussed today is the importance of chromatography towards green chemistry objectives. We showed features on the NextGen flash systems that help chemists achieve greener chromatography, such as our baseline correction and column recognition, and other safety features. One of the big things I hope you guys took away is how proper scaling can affect the reduction of overall solvent use. I think if we get chemists to choosing the correct column for the amount of material that they're using and not overdoing the purification and choosing a bigger column when they don't need to, you can make a real impact in the amount of solvent that you guys are going through in the lab. Also exhibited some alternatives to eliminate dichloromethane solvent use, taking advantage of the alternative solvent systems in stationary phases as choices. We've looked at different solvent choices in their green alternatives, such as the cyclopentyl methyl ether and 2-methyl THF as some alternatives that haven't been having widespread use, but as chemists become more familiar with them and the price of these solvents go down, they may become more advantageous to use from a green chemistry perspective and maintaining separation efficiency. And then we shared some other tips for implementing greener flash chromatography methods. So here's our Combiflash series of chromatography systems. On the upper left there, we have our NextGen 300 Plus and 300. And on the lower left, we have our NextGen 100, our base model. On the upper right, we have our Easy Prep Hybrid Flash Prep HPLC system and our high throughput torrent system on the bottom there for large flash separations. And all of these can be combined with our pure ion mass spec, which can be used to do mass-directed fractionation, and also you can basically turn your runs off or tell it to stop your run after you've recovered the mass of interest. So you can be green in that sense too, and use that as a tool if you have the pure ion. If you guys go to that link there, you guys can get our guidelines and tactics for flash chromatography, effective organic compound purification. It's a good book. Going to give you basics on organic compound purification using flash chromatography. It's got a lot of great information in it. We have some upcoming webinars. The end of the next couple of weeks here, December 6th, Jack Silver, my colleague, will be presenting the basics of prep HPLC. So that should be a good webinar where you guys can ask some good questions and get some good information from Jack there about our prep HPLC systems and how you can improve your prep purifications. And then in January, date to be decided, I will be presenting utilization of ELSD for purification of poorly UV detected compounds. Here's a list of our references. If you guys would like a copy of this list, please just email us and we can get that to you. Otherwise, you guys can use this video to go ahead and reference that. And I want to thank you guys for your time. Appreciate you guys taking the time to listen to us, and hopefully you guys can take some ideas and implement them in the lab and help reduce the lab's impact and help make chromatography greener for everybody. So thank you for your time. I appreciate it. Have a good rest of the day.